Welcome students. In this module, we are going to discuss about indicator diagram for reciprocating pumps. Now, before going to that indicator diagram concept, let's revise the functioning of reciprocating pump. Okay, we already know it's nothing but a positive displacement pump. Here, this piston moves front and back. It acts like just syringe, which is used for injecting medicines in our blood. Okay, so it acts like a syringe only. It's a suction valve. If this piston is at this position, both valves will be closed. When this position is at A, this piston will be at this end. Okay, if it comes to B, okay, it comes to half the way. That means suction pipe opens, water fills this piston. Okay, if this crank reaches C position, it is full open, so the entire piston is filled with entire cylinder is filled with water. Then suction valve closes. If move from C to D, it again this piston from this position to moves to center position. That means pushes off of the water. Delivery valves open, then water flows upward. Like this, during suction valve opens. During delivery valve will be closed. During delivery valve will be opened and suction valve will be closed. Like this only, this reciprocating pump is acting. Okay. Due to this, this is called length of the crank. Okay, during the traveling of this length, okay, there is some variation in pressure. For example, we know suction pressure always less than atmospheric pressure. Because we know, because if a pressure is less than atmospheric, then only suction happens. Okay, at delivery, pressure will be greater than atmospheric pressure. Okay, we can simply say during suction, okay, there will be negative pressure, so its pressure will be less than atmospheric pressure. During delivery, pressure will be higher than its atmospheric pressure. Okay, now because of this movement, because of this piston movement, there will be a variation of pressure at both delivery and suction side because of this movement. Okay, because during this movement, if it goes backward, it sucks water. If it moves front, it pushes the water. So that extra acceleration causes the extra pressure variation in both delivery valve and suction valve. We are going to represent that suction valve and delivery valve pressure variation with respect to this stroke length. That diagram is called indicator diagram. Okay, for example, if no acceleration, but acceleration will happen because it moves in simple harmonic motion. At start, its velocity will be 0, then increases gradually, then it becomes 0, then again it increases gradually and becomes 0. So like that, it moves in, with variable velocity. Due to that variable velocity, there will be surely acceleration. But if for simplification, if we know acceleration, then we can simply draw, this is head pressure head. I am taking this as stroke length. Okay, I know it is atmospheric pressure. Okay, I am taking this as HATM. I know at suction pressure will be less than HATM, so I am marking here this as H at suction. Okay, like that at delivery pressure will be higher, so I am marking here it as H, this value as H delivery. Okay, so during if I didn't consider any acceleration, then there will be a motion. Because of this motion, its hs will remains constant throughout the stroke length, like that. HD means delivery head pressure, it also remains constant. So if I join this is called indicator diagram. This indicator diagram indicates very simple thing. It indicates pressure variation with respect to stroke length. If there is no acceleration, there will be no pressure variation in suction head and delivery head. So delivery head and suction head pressures will be constant for no acceleration case. If I calculate area of this diagram, it will give area of diagram will be in rectangular shape. Area of diagram equal to I am taking this as HT, this is HS. So height of the rectangle will be HD minus HS, that is height of the rectangle. Then width of the length is stroke length. So this is area of this diagram, which is almost okay. If I am taking work done by pump, work done by centrifugal pressure, work done by reciprocating pump, we know work done by reciprocating pump is equal to unit weight of times A L N, mean gamma Q, gamma times Q, Q means H. This H value will be equal to HS plus HT. Okay, if I compare these two things, what I will get is here this HT is different. Okay, I am again mentioning this is atmospheric head. So I am measuring, I am making one simple correction. HT is nothing but increase in pressure comparing to atmospheric. Okay, HS is nothing but decrease in pressure with respect to HATM. That means pressure at suction head will be equal to HATM minus HS. Like that, pressure at delivery head will be equal to HATM plus HT. Okay, if I use this, then I'll get area of indicator diagram as like this. So work done will be is equal to gamma Q, this head. So this work done is directly proportional to this area of indicator diagram. Okay, I am again repeating. First I marked this as HS. This is not HS. HS is nothing but variation in with respect to atmosphere. That means this HS is not absolute pressure. Okay, we having two types of pressures. Okay, we having two types of pressures. One is absolute pressure, then another one is gauge pressure and vacuum pressure. This HS is vacuum pressure, this HT is gauge pressure. So actually absolute pressure at suction will be equal to HATM minus HS. Like that, absolute pressure at delivery will be is equal to HATM plus HT. Okay, so by this what I can say, what we can conclude is area of indicator diagram will be directly proportional to this work done. So this indicator diagram gives one proper idea about variation in its pressure, I mean variation in its head with respect to stroke length movement. Okay, now let's see the variation of this indicator diagram with variable acceleration. Okay, we already know because of that variable acceleration we derived suction head and delivery head pressure due to this acceleration variation is nothing but stroke length divided by G into A. Capital A is nothing but area of piston, small a is nothing but area of pipe, omega square into R cos theta. This R is crank radius. Okay, we already derived this formula in last unit itself. If theta, here theta is variable, if theta is 0, then this HAS and HAD both will become, because if at theta equal to 0, cos 0 equal to 1, cos 0 equal to 1, so this value becomes LS by G, A by A into omega square R. If this theta becomes 90 degree, theta becomes 90, this HAS or HAD will become LS by G. We know cos 90 is equal to 0. So LS by G into A divided by A omega square R into 0 is equal to 0. Okay, so at center, that means if this crank comes to center position, its value, both acceleration effects in both section and delivery will become 0. If theta equal to 180, then we will get the same equation with negative sign, because cos 180 equal to minus 1. So HAS or HAD will be equal to minus LS by G, A by A omega square R. Now let's see the indicator diagram. Okay, actually without acceleration, we already know this is stroke length. Based on this stroke length, this heads will change. At center, we know H atmosphere. Okay, but how it will come in general without acceleration means this is suction head at a suction pipe, so its value will be lesser. So without acceleration it remains constant. Like that, this is gauge pressure, this is vacuum pressure, this is gauge pressure delivery, its value will be higher. So this is delivery line pressure variation, this is suction line pressure, suction pipe pump pressure variation. Now let's we already discussed. Now we just come to one basic logic. During, if theta is equal to 0 degree, if I am taking theta equal to 0 degree, what will happen? At theta equal to 0 degree, that piston will be at this position. That means the piston will be at this position. At this position, what will happen? If in this position means, if you see, this is delivery pipe, the delivery valve, this is suction valve. Okay, this is suction valve, this is delivery valve. At starting, it sucks. So because of its suction, it creates negative pressure at both delivery valve side and suction valve side. Because of the increase in this suction valve will get advantage. At delivery valve, there is no advantage. So at delivery valve pressure, there will be some drop. So this is called HAD. Everything value will be same like that. But here also pressure decreases, but this decrease in pressure is advantageous, because of this there is a more suction pressure. It causes more water to come out. So there will be some drop in heads. Okay. After that, at 90 degree, we saw there is no variation at that means at LS by 2. There is no influence of suction pressure and delivery pressure due to acceleration. So here that value becomes 0. But if I am seeing at a theta equal to 180 degree, that means if a piston is here, if it start moving, what will happen? It causes both because of this positive movement, it causes positive pressure at both delivery valve and suction valve. So it will be advantageous for delivery valve, but due to this positive moment, there will be a decrease in negative pressure at this suction valve. So it causes little decrease. This value is HAD. like that. This value also HAD. So if we join, we will get indicator diagram for a variable acceleration. Okay, by this what we saw is, because of this acceleration, it indicator diagram changes, and also it causes the advantage. Okay, during suction, what will happen during suction? It increases the suction pressure, decreases the delivery valve pressure. During delivery, it increases the delivery valve pressure and reduces the suction valve pressure. Okay, so by using this, what we can conclude is, here also area of this indicator diagram will be is equal to work done only. Okay, so this indicator diagram for what we are using means, we know how to calculate theoretically power. What is the power? We know how to calculate power of any pump. By using this indicator diagram, we can calculate its power graphically. Okay, that is one of the advantage of indicator diagram. Okay, this is another LS by 2. Okay, with this I am concluding concept about indicator diagram. With this we are completing reciprocating pump unit also. Okay, thank you.